So let's turn our attention now to section 14.4. We're talking about centers of mass and moments. This is a topic that we first see in Cal 1, where we are looking at, in Cal 2, when we're looking at a solid region, and we're looking to find its center of mass. Now, in Cal 1, we assume that these objects are uniform in density and thickness because we, don't have the ability to do otherwise. Here we assume that this object is made entirely of the same material all the way through and has the same thickness uniformly throughout. But, what if this doesn't have a uniform thickness? What if it doesn't have a uniform density? Well, you could think of each point on this as having its own different density, its own different mass density. We say, okay, well, how would that work? Well, that's a function of two variables. After all, this is just a plane on the XY plane. That's a region on the XY plane. Here, they use the physics term, a planar lamina. And if every point on here has a different density, well, then this point has a particular density that we could find based off of that point. But that's a function of two variables. So here, the density at any point is a function of two variables, because it's a function of the point of the location on that planar lamina. Okay, so our object might look something like this, where it might be more dense toward the middle, and as you move out, its density decreases. So the darker shade represents a higher density, whereas the lighter shade represents a lighter density. So now here, our center of mass would be, somewhere toward the middle. But that's because everything here is uniform. On the other hand, here, if most of the weight is concentrated here, that means even though there's more material over here, it's going to have less weight. So our center of mass would move closer to this point. So that brings us to some definitions here. This doesn't require any new math. This is an application of what we've seen in the last few sections. Here we have a definition. Let rho be a continuous density function. So here rho is actually a function of two variables, as you see here. Let it be a continuous density function on a lamina corresponding to a region R. So we have some region, which we're going to call R, and on that region, every point will be given its own density. That density will be based off of what point on the region you have, and so that density will be a function of those two coordinates. Or in other words, it'll be a function of x and y. All right. So here we would have, rho of x comma y gives the density. Okay. That is going to give us our mass. Because if we take our density and we add up the amount of stuff at every point and put it all together, that's going to tell us the total mass of our object. So the mass is simply given by the double integral over the entire region of the mass density function over the area of the region. All right? Now, the moments with respect to the x-axis and to the y-axis, you'll remember in Cal 2 that take a bit of effort because we had to describe all of this with respect to a single variable. In Cal 1 and 2, we don't really have the ability to express things in terms of multiple variables. Here, we have to express everything in terms of x. So our moments, you'll think back, were a little bit more complicated looking. But now, since we can express everything in terms of any number of variables we like, the expression is now much simpler. The moment of mass with respect to the x-axis, if that's the x-axis down here, then the moment at a particular point is simply given by, the moment at a particular point is simply given by the distance from the x-axis up to that point. Oh, but the distance from the x-axis up to a point, well, that's given by its y value. So here we're going to take y times the density, and if we add up the moments of every point, then total, that gives us the moment of the entire lamina with respect to the x-axis. Likewise, if I want to find the moment with respect to the y-axis, well, here's the y-axis, and the moment of mass of a point is given by its mass times the distance from the axis. So here, the distance that I want is the distance from the y-axis, but by definition, that's just the x-coordinate. The x-coordinate tells you how far you are from the y-axis. So here that'll be, well, we want to take the product of the distance times the mass. Well, there's the distance times the mass right here. Yeah, it's going to give us our mass. And now we add all that up for every point on our region, and that gives us our moment with respect to the y-axis. So this isn't any different than the definitions of moments were for previous chapters. Rather, because we're now able to express things in a function of multiple variables, we now have a much simpler setup, which gives us some much nicer looking problems, or rather, some much nicer looking results to our problems. So let's take an example. Let's consider the following region. We're going to define a region as the stuff, as the area that's bound between y equals x squared, y equals 0, and x equals to 2. And what we want to do is we want to take the center of mass of the region bound by these functions, which has a density function, and our density function is going to be rho equals k, rho is going to equal to kxy. Now remember, rho is a function of x and y. So you might ask, well, what is k? Well, k is just going to be a constant. And that constant would, in a physical example, if we were actually looking at some material, it would depend on the material we were looking at. If these laminas were made of steel, of iron, of cardboard, well, then we'd have different values of k depending on the material. But for now, that's just a constant. Okay? So here, we're going to go ahead and find the center of mass. And note that the center of mass is simply found by finding the mass, finding the moments, and dividing. And yes, I know this looks backwards. It looks like it should be mx and my, but that is the way these are defined. That is the way the notation is defined. And frankly, I don't like it either. But this is something we borrow from physics, and well, we don't have any control over their notation. So let's go ahead and compute this stuff. First of all, let's start with our mass. Our m is simply going to be given by the double integral over the region R of rho x comma y dA. Well, notice we have a region that we have been given, and that's just y equals x squared. Okay, well, that's a parabola. Y equals to 0. Okay, well, that's the x-axis. And x equals to 2. Well, that's this number right here. That's 2. Here, if x is equal to 2, y is equal to x squared, so that would be 4 up here. And now we want all the stuff inside of that region. All right, so that's going to be our region there. Let me erase this part. It's not going to be necessary. And what we're looking at is just this region here, beneath this parabola and between these two straight lines. Okay? All right, so now we note that we have a density function of x times y times a constant. The constant is a constant, so let's not worry too much about that. Notice that these are variable. So note that as you get closer to the origin, as you get closer to 0, 0, your density tends towards 0. But as you move away from the origin, these numbers get larger, and so your density gets higher. So here, if we were going to draw this to reflect the density, I would draw it with a higher density over here, and as we move toward the origin, our density drops off lower and lower. So here the darker color represents a higher density, and the lighter color represents a lower density, something like that. That's not particularly important to have that drawn out, the shading. This is just for a visual at the end, so we have something to compare to for the purposes of the explanation. All right, so now I'm going to go ahead and write this. We can express this in rectangular coordinates. This doesn't look like something that we really need polar coordinates for, although in certain problems we could. It may be more convenient to use polar. But here, y equals x squared seems perfectly good in a rectangular form. So here, let's go ahead and take our density function. That's going to be kxy. And we'll do this with respect to y and then with respect to x. Okay? So now y, we're describing the lowest and the highest values of y. Notice that the lowest value of y you can get is just the x-axis, or in other words, y is equal to 0. The highest value you can get, notice that's variable. Here, you don't go very high. Here you go higher, and here you go very high. So it's based off of this boundary. It's based off of x squared. Okay, so then the highest y you get is this upper bound. Is this y equals x squared. Remember, when you use an iterated integral to compute something, this outer set of integration must be with respect to only constants. So here we're going to describe x with using only constants. The smallest value that you ever get for x is going to be 0, and the largest is 2. And that shouldn't take too much effort. If we integrate that with respect to y, that's going to be the integral from 0 to 2, like that. And now this part here would be kxy squared over 2. Notice we don't really worry about the k or the x because with respect to y, those are just constants. So here we're left with just the integral of y, which is y squared over 2. The k and the x are just constants that follow along. And now we're going to set y equal to 0. We're going to set y equal to x squared, and then we will subtract. So now that's going to give us the integral from 0 to 2. If we set y equals to x squared here, well, that's going to be x squared squared, which is x to the 4th, times another x is x to the 5th. Like that. If we set y equal to 0, well, that's going to be k times x times 0 over 2. And, of course, anything times 0 is 0, so this part just goes away. That's 0. And so we're left with the integral from 0 to 2 of kx to the 5th over 2 dx. And that's a nice simple integral that we can take. We integrate that. We can now say that's x to the 6th over 6. Now, of course, it's already got a 2 down there, so that's going to become kx to the 6th over 12. And we're evaluating that from where x is equal to 0 up to wherever x is equal to 2. All right, so now we can go ahead and evaluate. If we substitute in 2 right here, 2 to the 6th power, that'll get us 64. So that's going to give us, let's see, k times 64 over 12. Of course, substituting in 0 makes this whole thing 0, so we don't worry about that one. Let's see, 64 over 12, we can reduce that. We can divide the top and bottom by 4, so that'll give us 16 over 3. So 16k over 3. All right, so there is our mass. So now we can take a look at our moments, because they are very similar to the current integral that we're taking, except that for a moment with respect to the x-axis, we multiply here times y, and for a moment with respect to the y-axis, we multiply here by x. All right? So this is going to continue. We're going to go ahead and say, okay, let's try our moment with respect to the x-axis first. The moment with respect to the x-axis is given by the double integral over the region R of y times rho x y dA. And we know that the moment with respect to the y-axis is given by the double integral of r times x rho of x comma y dA. Okay, let me go ahead and split this. Should be able to get them both in here. All right, so now this can be written as, well, that's the double integral over the region R of, well, we said that rho is k times x times y, but now that's another y, so that'll be kxy squared. And same thing over here, that's going to be the double integral over R, and that's going to be k xy times another x is k squared, is k times x squared y. So you'll note that these are really rather similar. At this point, you might want to pause the video and give these both a try. Remember, we still have our region R. It's still the region that we had before, this one here underneath the parabola. So you might want to give that a try, and when you've gotten to a place that you have an answer, unpause the video and we'll finish this off. All right, so let's take a look here. We're going to go ahead and use the same boundaries of integration that we had before. It is the same region after all. So this is still from 0 to 2. This is 0 to x squared, kxy squared. Here, this is with respect to y first, and then with respect to x. We're reusing all the same boundaries as before. The only thing that's changing here is the integrand. Likewise here, that's going to be the integral from 0 to 2, the integral from 0 to x squared, kx squared y dy dx. All right. So now if we integrate with respect to y, this now becomes the integral from 0 to 2 of just this part in here. That's going to be k x y to the third over 3. Like that. And that's going to be evaluated from y equals to 0 up to y equals to x squared dy. Well, now that's equal to the integral from 0 to 2. Y equals to 0 makes that 0, so we don't worry about that. But if y equals to x squared, well, x squared to the third, well, that's x to the 6th times another x, would be k x to the 7th over 3. Just like that. And now if we integrate that with respect to x, we're left with kx to the 8th divided by 8, but there's already a 3 down there, so that's going to be 24, evaluated from wherever x is equal to 0 up to wherever x is equal to 2. Right? If we substitute in 0, that makes the whole thing 0, so we don't worry about that one. Let's just worry about substituting in 2. 2 to the 8th power over 24. Okay, well, 2 to the 8th power, that'll get us 256. We still have our k here, over 24. And we can divide each of these, top and bottom, by 8. And that'll give us, oh, let's see here. That'll give us k. Divide the bottom by 8 gives us 3. And divide the top would give us 32. So there we go. So this will give us 32k over 3. Over here we get something a little different, but the mechanics are very much the same. Here we're going to integrate with respect to y first, and that'll give us k x squared y squared over 2. Our constants are going to be a bit different from one problem to the next. So now here we're going to evaluate this as y goes from 0 up to y equals to x squared. We still haven't performed our second integral, so let's go ahead and leave that intact. If we set y equal to 0, the whole thing is 0, so we don't worry about that. If we set y equal to x squared squared is x to the 4th, times another x squared is x to the 6th. So that'll give us k x to the 6th over 2. And now we're going to go ahead and integrate this with respect to x. Okay, well, we'll raise that to the 7th power. So this will now be kx to the 7th power over 7. But there's already a 2 down there, so that's 14. And that's going to be evaluated from 0 up to 2. So obviously, if we plug in 0, that makes the whole thing 0. But if we plug in 2, well, that'll give us an answer. That'll be k times 2 to the 7th over 14, which is k times 128 over 14. And that can be reduced. We can divide top and bottom by 2, and that'll give us 64k over 7, just like that. So now we're just about done. Remember that your center of mass is given by, you're going to take the moment with respect to the y-axis over the mass, comma, the moment with respect to the x-axis over the mass. Okay, well, we know both of those. The moment with respect to the y-axis is going to be 64k over 7. The moment with respect to the x-axis is going to be 32k over 3. And now we're going to divide both of those by the mass, which we found in the previous stage. We found the mass to be 16, right here. We found the mass to be 16k over 3. So we're going to go ahead and divide everything by 16k over 3. Remember, when you're dividing by a fraction, that's the same as multiplying by the reciprocal. So instead of saying I'm going to divide by 16k over 3, I'll say I'll multiply by 3 over 16k. I'll go ahead and use the reciprocal. And there we go. We can simplify this quite a bit. You'll notice that one of the reasons we don't really care about what this constant is because in most of our computations it doesn't matter. If we're finding our moment and if we're finding our mass, of course it does. But here, when we're looking for our center of mass, it doesn't really make a difference. And now some of our other numbers work out rather nicely. Here, let's see, 16 goes into 64 4 times. So that's going to be a 4 right there. And that looks like that's all that simplifies. Here, 16 goes into 32 2 times. And that looks like that's all that simplifies. So putting that all together, that's going to give us 12 in the numerator, 7 in the denominator, comma. Let's see, this will give us, I didn't even notice that. Here, these 3's divide away. And so we're just left with everything divides away except for the constant 2. And here is our center of mass. As a quick sanity check, let's go ahead and look and see where this point rests on our graph. We saw our graph earlier, and this is a little small. Let me go ahead and blow that up. Our graph is let's see here. That would be about 1, 2, 3, 4 here. And our graph is straight up this way and then curved right along here. Okay, so we know that it's denser away from the origin, and it gets less dense as you move toward the origin. All right, so let's see where this point lies. 12 over 7. That's going to be 1 and 5/7. So to the right, 1 almost all the way to 2. And then you're going to go up 2 steps. So right around there. That will be 4, 3, 2, and 1. 1 and 2. So as a quick sanity check, first of all, if your center of mass is over here, up here somewhere, that's probably not right. There are some interesting cases where the center of mass is not inside your region. It is possible to be right on the edge or even slightly outside of the region. But here, this does look about right. There's more material down here, but it's less dense, which is counteracted by the smaller amount of material here, which has a higher density and therefore a higher mass. So just as a quick sanity check, it does look about right. It doesn't seem like we've made any major errors. And double checking, it does look like we are correct. And I hope you all don't mind, but that really is it. That's the entirety of this section that we're going to be looking at. We've seen one example of how this works in full, the mass along with the two moments. This section is not meant to give you any new material in terms of calculus. Rather, it's just an application to make sure that we can use some of the things that we've already seen, in particular using the double integral. So that really is it. As an assignment for the section, go ahead and try, let's see, this is 14 point, oh, what are we doing? 14.4? Go ahead and try 13 through 21 odd. And that'll suffice. Okay. That is it for the section, and I hope you all have a nice day.